Hello, welcome to Key in Motion's course on understanding electricity and electronic devices. Today, we're going to talk about MOSFET transistors. Let's start by reviewing some concepts that we studied in previous classes. We learned that bipolar transistors are available in two polarities, which are NPN and PNP. And we learned how to use them in switching applications, where an NPN transistor acts as a switch to the negative side of the supply, and a PNP transistor acts as a switch to the positive side of the supply, right? Sometimes called sinking output and sourcing output, respectively. And many times PNP are used in combination with NPNs. For instance, in an H bridge to control the direction of a motor. Today, we're going to talk about MOSFETs, which is a different kind of transistor. There are different types, and we're going to study some electrical characteristics and how to use them in some circuits. MOSFET stands for metal oxide semiconductor field effect transistor. That is a lot of words and they don't mean much, so everybody just calls them MOSFETs or just MOS transistors. They're used in digital electronics like computer chips. Those have millions of these transistors in a chip for a big processor like the one on your laptop or your phone. They're used in power electronics as well, right? And they have better performance than bipolar in high power switching applications. So they have some advantages. And they also can switch faster than bipolar. So if you have an application where you need to switch high power, high current, and you need to switch that fast, usually a MOSFET is going to be a better option than a bipolar transistor. Let's see what a MOSFET looks like. They look from the outside the same as a bipolar transistor, right? So this is taken from a data sheet. This is an IRF 540N, right? So if you recall, this type of package was also used on bipolar transistors. So just by looking at the transistor, you cannot tell whether it's a bipolar or a MOSFET. The same as bipolar transistors were available in NPN and PNP polarities, the MOSFETs are available in N-channel and P-channel, right? So this is the symbol on the top, the symbol of an N-channel MOSFET. This is roughly equivalent to an NPN transistor, okay? We're going to study the differences in a few minutes. This one here at the bottom is a P-channel transistor, a P-channel MOSFET, and it is roughly equivalent to a PNP transistor, okay? Now, something to keep in mind is the direction of the arrows are reversed with respect to the bipolar, right? So this is the N-channel MOSFET, and the arrow points in, right? And we said this is equivalent to the NPN, and in the NPN transistor, the arrow from the emitter was pointing out, right? So keep that in mind. The arrow is in the opposite direction. Now, the terminals on a MOSFET are not called emitter, base, and collector, but are called drain, source, and gate, okay? Drain, source, and gate. The gate is the one which is by itself, which is the one that's going to be controlling the current through the drain and the source. We're going to see that in the next slide. And the source, you'll see it's the one that is that has like kind of these two terminals connected here. This connection here, this part in the middle is called the substrate, and it is internally connected inside the transistor to the source. So the source is the one connected to the substrate. So it's the one that has like two terminals connected together. That is the source. The one that is by itself is the drain, and the gate is on the other side, okay? Same here, only the arrow is reversed. Now, let's have a look at the MOSFET model. Remember, in bipolar transistors, the base current was controlling the collector current. In MOSFETs, it is the gate voltage, not the current, what controls the drain current. So the model is going to be something like this, right? Remember, on the bipolar, we had a diode between the controller terminal, let's call it like that, which was the base, and the source or the emitter, right? And here we have nothing between the gate and the source. It's simply the voltage. And this voltage is going to be controlling the current through the drain terminal, right? And a variation of the drain current is going to be controlled by a variation on the voltage between gate and source, okay? Multiplied by this parameter, which is GFS. GFS is called a transconductance, and it's measured in amps per volt, or Siemens, which is this capital letter S, or milliamp per volt, or millisiemens. Also, they require a minimum gate to source voltage to start conducting. Remember, on the bipolar, you had to forward bias the diode, so the voltage between the base and the emitter would be 0.7 volts, right? You would need at least something, at least about 0.5 volts to make that transistor to start conducting, and about 0.7 volts to make it conducting a current that it's going to be useful for you, typically, right? MOSFETs do not have a diode there, but they do have a minimum voltage that they have to have between gate and source. That voltage is called the threshold voltage, and is symbolized as VGS-TH. So this is the threshold voltage between gate and source. MOSFETs are most commonly used as switches. So let's see how we use a MOSFET in a circuit. Here we have a circuit with a 24-volt power supply connected to a motor, and then the MOSFET connected to ground, and some kind of controller that will output 0 or 5 volts to turn on and off the transistor, and therefore the motor. Normally, you do not require a resistor between the controller and the gate, because there's no current flowing through the gate that you have to limit there. So you can connect it straight to your controller. Now, there's some special high switching applications, or sometimes some conditions in the circuit make it better to put a small resistor here, maybe about 10 ohms or so, okay? Just be aware of that, but normally this is not required. Now, one potential problem that we may have with this circuit is that for the transistor to turn on, we need at least the threshold voltage. And the threshold voltage can be very close to the 5 volts maximum that this controller can deliver, right? So this is something to keep in mind. And especially with higher power transistors, they may need a higher gate voltage to turn on. And we may have to add more circuitry here between the controller and the transistor. But we're not going to get into such details. Just be aware that that's a possibility. As usual, when switching an inductive load, we want to have this diode here in parallel to make sure it will provide a path for the current to flow when the transistor turns off quickly. Now, a couple of precautions that you have to have with MOSFETs. One is to not leave the gate unconnected, okay? And why is that? Let's consider this circuit, right? So we have the same controller, the same circuit as the previous slide, but the controller somehow, this is symbolizing a connector here, the female side and the male side. And this is connected to the gate of the transistor and the controller. So maybe we can disconnect the controller from the gate. Now, this is something you have to avoid. And why is that? The gate actually acts as a tiny capacitor there. So remember, capacitors can be charged to a certain voltage, and then they will stay at that voltage, right? So if this gate is on and you disconnect here, this gate is going to remain on, okay? So you may want to keep a resistor connected to ground over here to discharge the capacitance of the gate whenever this thing is disconnected, and ensure that the transistor turns off. If the controller cannot be disconnected from the gate, this is not necessary. All right. This is called a pull-down resistor because it will pull the voltage down, or the charge from this point down to ground. Okay. If this was connected to positive, it would be called a pull-up resistor. The other thing that you have to keep in mind is that MOSFETs are sensitive to ESD, or electrostatic discharge. Although some are protected. We mentioned that MOSFETs are used in quantities of millions in computer chips. Now, computer chips are also sensitive to ESD, but the inputs are usually protected. MOSFETs, discrete MOSFETs, they are not. So be careful when handling MOSFETs that are not already installed in a circuit, because those are very sensitive to electrostatic discharge. So make sure you ground yourself and you discharge any static electricity that you may have. Once they are inserted in the circuit, there are different paths for any possible electrostatic discharge to flow, and that will help somehow protect the MOSFET. But it's still always a good practice to ground yourself when working with circuits to avoid electrostatic discharge. Let's see some electrical characteristics of the MOSFET. We already talked about VGS-TH, or the threshold gate source voltage. That's the minimum voltage between gate and source for the transistor to start conducting. And our parameter is RDS on, right? So this is the resistance from drain to source when the transistor is fully on. Remember, MOSFET transistors are many times used in switching applications, so they are characterized by an on-off state. The other one is GFS, which is the transconductance, that is the change in the drain current in amps per volt that changes in gate source voltage, okay? The table below is taken from a data sheet, and we can see some of the characteristics. The first one we see here is a drain to source breakdown voltage, minimum 100 volts. So that means this transistor can withstand 100 volts between drain and source. The other one we see here is RDS on. It's the static drain to source on resistance. It's the one I was mentioning here. And this one is rated at 44 milliohms, or 0.04 ohms, okay? The other one is the gate to source threshold voltage, and it is specified at a minimum of 2 volts and a maximum of 4 volts. Again, this is to get a drain current of 250 microamps. So 250 microamps is a tiny current for a drain. Remember, this transistor can switch several amps, right? And we're talking here a quarter of a milliamp. So this is when the transistor is barely starting to conduct. So the manufacturer guarantees that the transistor will turn on at 4 volts, but 4 volts is not nearly enough, or may not nearly be enough to switch on the load that you want. We're going to have a look at some curves here to understand what voltage we want to put on the gate to actually make this work properly. And the last one here is the forward transconductance that I was talking about. And it is rated at the minimum of 21 Siemens or 21 amps per volt. So this means that for every volt that we change in the gate voltage, the current through the drain, if the circuit allows it, is going to change in 21 amps, okay? So let's have a look at some on characteristics of this MOSFET. This is the part number that I used as an example, and I'm taking this graph from the data sheet. So let's have a look at this graph. This graph plots drain current, right? ID, and this is VDS, the drain to source voltage, right? So this is how much voltage we are losing on the transistor. We want the transistor to behave as a switch, to be completely on. So we want the transistor to be in this area, right? Between 0.1 volts and 1 volt, maybe. And if we can keep it even lower, it's even better, okay? We have several curves here. These curves are for different values of VGS, or gate source voltage. So they start at 4.5, right? The second is 5 volts, 5.5, and so on. Now, let's assume we want to switch a 10 amp load, okay? So 10 amp load, that would be over here. We want 10 amps flowing through the transistor, right? So we're going to be somewhere in this area. Now, this leaves the 4.5 volt curve pretty much out of the picture, because at 10 amps, right, this is intersecting the 4.5 at 1 to about 3 volts here, right? And we want to be less than 1 volt and less than half a volt if possible. So we're going to be working in this area. So the minimum gate voltage that we need to switch this 10 amp load, it's going to be 5 volts, okay? So even if the threshold voltage for this transistor was 4 volts, as you saw on the previous slide, we need at least 5 volts to have it where we want it, right? I would not recommend this transistor if you want to switch 10 volts and you only have like 5 volts available to switch it on, right? So you would have to insert some kind of circuit that can provide a higher voltage to the gate, or use a different transistor. Okay, so if we want to select a MOSFET for switching, the characteristics that we have to keep in mind are the maximum VDS, so the maximum voltage between drain and source that the transistor can withstand when it is off, then the maximum drain current that the transistor can withstand when it is fully turned on. RDS on, which is the equivalent drain to source resistance when the transistor is fully on. We want this number to be as low as possible. In the previous example, it was 44 milliohms, so 0.044 ohms, that's fairly low. And then the VGS threshold, which is the voltage at the gate for the transistor to turn on, and the voltage at the gate at the required current drain that we are planning to use the transistor. Let's do a quick recap of what we saw today. Today we studied the MOSFET transistors, and we learned that they are available in N-channel and P-channel configurations or polarities. We learned that the gate voltage controls the drain current. We learned that they have no gate current to maintain the transistor on, but remember, because the gate acts as a tiny capacitor, you need some current to charge and discharge the capacitor. and MOSFETs are best suited for applications requiring high current or fast switching. Okay, that is all for today, and this is actually the last class of the course, Understanding Electricity and Electronic Devices. I hope you enjoyed it, I hope you learned a lot, and we'll see you in the next course. Thank you, goodbye.